Good morning, students. In previous class, we discussed about to calculate the density of a solid. So, density of a solid can be calculated by using the formula D is equal to Z into M divided by AQ into NA, where Z is number of atom and M is molar mass of the solid and A is edge length and NA is nothing but the Avogadro number. So you can work out another one problem. Say in a cubic lattice you can find if a solid shows has mass, its molar mass 2.7 into 10 raised to minus 2 kg per mole. Its edge length is 405 picometer, and density is again 2.7 into 10 raised to minus 3 kg per meter cube. Find the nature of unit cell. See, this indicates that in a solid which has a molar mass 2.7 into 10 raised to minus 2 kg per mole and its edge length is 405 picometer. Density is given 2.7 into 10 raised to minus 3 kg per meter cube. And we have to find the nature of the unit cell. See, we can find the nature of the unit cell by finding the number of atoms. If suppose number of atoms we got 2, it is nothing but a body centered cubic unit cell. If it is 4, then it is nothing but a face centered cubic unit cell. If we got Z is 1, that is nothing but a primitive or a simple unit cell. So we shall work this problem. So in a given problem, either it may be a metallic solid, its molar mass is given, density is also given, and edge length is given in picometer. Are you clear? So we have the formula D is equal to Z into M divided by A cube into NA. So which is nothing but to calculate the density. So you have to calculate here number of atoms. That means Z you have to calculate. First we shall see what are the notation given here. So molar mass M is given. See, M is equal to 2.7 into 10 raised to minus 2 kg per mole, which is in SI unit. And again, edge length is nothing but 405 picometer. Convert this into meter. So it is nothing but 405 into 10 raised to minus 12 meter. 10 raised to minus 12 meter. And it will become see 4.05 into 10 raised to minus 10 meter. So 1 picometer is equal to 10 raised to minus 12 meter. Don't get confused. 1 nanometer is equal to 10 raised to minus 9 meter. 1 picometer is equal to 10 raised to minus 12 meter. Just try to convert that. We have density D is also given. It is nothing but 2.7 into 10 raised to minus 3. So we have the formula D is equal to Z into M divided by A cube into NA. Derived in terms of Z. So Z is equal to, so you will get Z is equal to, say D into density into A cube into NA divided by molar mass. Are you clear? So in terms of number of atoms. Now easily you can substitute the value. So what is the density is given, which is nothing but 2.7 into 10 raised to minus 3. So kg per meter cube. And again, edge length, see edge length 405 picometer, which is nothing but 405 into 10 raised to minus 12 meter. Then at 4.05, 2 decimals, it is 10 raised to minus 10 meter. So you will get, which is nothing but a cube 4.05 into 10 raised to minus 10 the cube into Avogadro number you know 6.022 into 10 raised to 23 divided by we will get molar mass is given, that is nothing but 2.7 into 10 raised to minus 2. Say it is nothing but kg per mole. So you can easily work out this. A simple substitution, that's all. According to formula, you are substituting the value. Are you clear? Very simple. See, 2.7 into 10 raised to minus 3 kg per meter cube. 4.05 into 10 raised to minus 3 into 6.022 into 10 raised to 23. And here it is nothing but the molar mass. Molar mass value is given in the problem. So you substitute here, just you calculate it is nothing but 23, and you will get nearly 3.99, which is equal to 4. As we got z is equal to, we got in this problem we got z is equal to 4. Are you clear? Just use calculator and you will get nearly value 3.99, and that is which is equal to 4. Z is equal to 4. If it is z is equal to 4, what is the nature of unit cell? See, it is nothing but a phase center cubic unit cell. So it is nothing but a phase center cubic unit cell. Okay. So writing the appropriate formula, you will get 1 mark. Then whatever the given values, right? And if any conversion, you can do. Repeatedly I am going to tell you 1 picometer is equal to 10 raised to minus 12 meter. Then just substitution, D is equal to Z into M, A cube into NA. Then Z is equal to D into A cube into NA divided by molar mass. As Z value we got 4, therefore it is a cubic unit cell. Are you clear? So like that you have to work many problems. It's simple, just value is changed. We concentrate the formula, substitution and calculation. You will get to calculate density and also you will get to calculate the number of atoms. That is the nature of unit cell. Okay. So we shall continue our discussion on imperfections in solids. Are you clear? See, repeatedly while sending the notes, number of problems is given in notes. You have to work out. Okay. So this is nothing but the calculation of density. We worked on one problem in the last class also. We shall study next part, which is nothing but imperfections in solids. Imperfections in solids. So which is nothing but defects. See, during the crystallization to form a solid, there must be some impurity, and that impurity is in traces quantity, very less quantity, but it affects the solid. During crystallization, that is nothing but a formation of solid. Some of the impurities, it may be other element, it may be other substance, which interferes in the lattice of the solid. and that particular phenomenon is called imperfections in solid. So, in this the arrangement of solid, while the particles are arranging, the arrangement is little bit separate, little bit different. No doubt, overall arrangement is same. In the cavities, in the spaces, certain particles enters, and such a phenomenon is called imperfections or defects in solids. There are two types of defects. One is point defect, another one is line defect. See, there are two types of defects. One is point defect, point defect, point defect, and another one is line defect, line defect. Are you clear? There are two types of defects. What are those? One is point defect, another one is line defect. See, according to your syllabus, you have to study the point defect. The regular arrangement particles are arranged in solid. During the crystallization, certain impurities enters. See, solids are formed when different atoms goes to gaseous state, it attracts, and then it forms a solid. At that time, during the recrystallization, and it has certain impurities. That particular phenomenon is called imperfections in solids. So here, point defect. What do you mean by point defect? See, according to your syllabus, you have to study only the point defect. See, in a lattice of a solid, certain particles are missing, or extra particles enters. That is called point defect. In a line defect. So particular one row is completely missed. That is nothing but a point line defect. So according to your syllabus, you have to study only the point defect. We should study what are different types of point defects. What are the different types of point defects? Are you clear? That is nothing but imperfections in solid. We shall study what are the different types of imperfections in solids. See, in point defect, we have, see, first one, stoichiometric defect. See, in the stoichiometric defect, we have again vacancy defect. See, vacancy defect. And P, interstitial defect. Interstitial defect. What are the two types of stoichiometric defects? Stoichiometric defect means where the stoichiometric number of particles and its all chemistry holds good. That is called the ratio of the combination of the particles, its molar mass, everything, that is called stoichiometric defects. And it has two types. One is vacancy defect and interstitial defect. Vacancy defect and interstitial defects are generally occurring in non-ionic solids. These are generally occurring in non-ionic solids. Are you clear? See, these are occurring in non-ionic solids. Non-ionic solids. See here, what do you mean by vacancy defect? See, these are the number of points where lies. See, one of the point is missing. See, this particular part, there is no particle, and one of the particle is missing during the crystallization, and this type of defect is called vacancy. What about density in vacancy defect? In vacancy defect, density decreases as one of the particle is away from the lattice. It is not in the crystal. A solid is nothing but a large amount of crystals we can find. In the entire lattice, see, this one of the particles is missing. And you can find there is a vacant, therefore it is called vacancy defect. In vacancy defect, density decreases. Density decreases. Why? One of the particles is missing there. There is a vacancy. Okay. We shall study interstitial defect. See, in interstitial defect, imagine it's a lattice. So we have certain particles arranged like this, and in this lattice only, one or two particles are arranged in the interstitial positions. In the interstitial positions like this, you can see. See here also. Can you see? In the rows of the column, where the points are there, particles are there, extra particles are there in the interstitials. In the interstitial. So such type of defects are called interstitial defects. See, in actual interstitial defects, the number of particles are more in the gaps in the space. Therefore, density increases. Density increases. Okay? So these are the basic two types of defects which you can find in point defect of the solid. One is vacancy defect, another one is interstitial defect. Are you clear? So we shall move on the different types of defects which arises in ionic solids. In ionic solids, we can find. See, in ionic solids, in ionic solids, we can find two important defects. One is Frankel defect. Another one is Scotty defect. See, Frankel defect. Another one is Scotty defect. Are you clear? There are two types of defects in ionic solids. If you go for Frankel defect, see, which both are arises in ionic solids. In Frankel defect, you can see easily. See, these are the particles which is present, and one of the particle is you can find here vacancy defect. Are you clear? And whatever the particle is missed in one point, in one line row, it is in the same solid, but it is present in another line. And you can find here a vacancy defect. It creates also an interstitial defect. And this type of defect is called Frankel defect. What about the density in Frankel defect? Density remains same. In Frankel defect, density remains same. Why? Because, see, one of the particle is missed at one position and it is in the same lattice. Here we can find the vacancy defect and here we can find the interstitial defect. What about density? Density remains same in the Frankel defects. Are you clear? In Frankel defect, density remains same. And we can say vacancy defect, and we can also say in another side it is an interstitial defect. Are you clear? Okay. Now you go for Scotty defect. And here this Frankel defect takes place in solids where cation and anion has different in size. There is a difference in size of cation and anion. We can find Frankel defect. If we go for Scotty defect, see here, equal number of cations and anions are missing. If suppose this is anion, cation, anion like this. So this is plus and this is minus. We can find equal number of cation and anions are missing in ionic solid. At that time, thus that defect is called what? Scotty defect. What about density? See, cation and anion are completely away from the lattice. Therefore, density decreases. Automatically, density decreases. So the examples we can find is HABr, again AgI, etc. So in Frankel defect we can find the example even KCl, NaCl, again AgBr. See here AgBr, silver bromide, exhibit, both Frankel defect as well as Scotty defect. So we will ask 2 marks question. Make the difference between Frankel defect and Scotty defect. So both these defects arises in ionic solid. In Frankel defect, the particle missed is present in the same lattice, so therefore density remains same. It arises in ionic solids when there is a difference in cation and anionic size. Okay. If you go for Scotty defect, in Scotty defect, equal number of cation and anion are missing. They are not in the lattice. So therefore, the density decreases. You can give an example. Example where silver iodide, silver bromide, and again in Frankel defect, you can find even NaCl, KCl, AgBr, ZnS. These are the different types of examples. Okay, then next we have to study the impurity defect. Impurity defect. Next one, which is second one. Impurity defect. Impurity defect. See, in impurity defect, during the crystallization of, particularly take example sodium chloride. During the crystallization of the sodium chloride, in that lattice, the sodium ion moves to the surface. As sodium ion moves to the surface, the negative anion, chloride ion, it also creates a vacancy in the lattice, and it also moves to the surface. And we can find there is a lattice. So this is nothing but one of the lattice is to remember. During the crystallization of sodium chloride, any strontium chloride is present as impurity. We can find, so this is nothing but a sodium, see Cl minus and Na plus. So this is Na, like that we can find. Where large number of sodium ions are. See, as all these are sodium ions. See, these are sodium ions, and one is replaced by strontium ion, Sr2 plus, and another will become vacant due to its charge. And this type of defect is called impurity defect. Example is, in the crystal of sodium chloride, the presence of strontium ion, Sr2 plus ion. Okay, as sodium ion moves towards the surface, the chlorine ion also. That means, as this sodium ion, at that time we can find the gap. So this strontium ion, it acquires two positions, and this is called impurity defect. Example is sodium chloride and strontium chloride. If you have another example is cadmium chloride and silver chloride. Just remember the example. Okay. Then we shall study the non-stoichiometric defects. So stoichiometric defects we studied, and next the third important one is we have to study the non-stoichiometric defects. Non-stoichiometric defects. Stoichiometric defects. In the non-stoichiometric defects, we have two important. One is metal excess defect due to anion vacancy. Are you clear? Metal excess defect due to anionic vacancy and due to cationic vacancy also. So we should study in sodium chloride crystal. In sodium chloride crystal, you can find in sodium chloride crystal. Say it is nothing but the lattice of sodium chloride. It is nothing but the lattice of sodium chloride. You can find here now. So this is nothing but a Cl minus and Na plus, like that. Cl minus, Na plus, Cl minus, Na plus, Cl minus, like that you can find. So here again, which is smaller one, which is bigger one, smaller one, bigger one, smaller one, bigger one, smaller one, like that it goes. See, carefully observe the diagram. Carefully observe the diagram. See, due to, if suppose this Cl minus during crystallization, again this anionic vacancy during crystallization of sodium ion, again sodium passes to the surface. We can find these are nothing but the plus. See, one anionic vacancy in the lattice, due to anionic vacancy, one of the gap is created, and which is filled by an unpaired electron. It is filled by an unpaired electron. Which is filled by an unpaired electron. You can see. So this is nothing but the electron. Are you clear? Due to anionic vacancy, so unpaired electron occupies the anionic site. Unpaired electron occupies the anionic site. That particular center is called F center. This F center, which is called a forbidden region, therefore it is called an F center. Are you clear? And it imparts color to a particular solid. So here, due to anionic vacancy, electrons are occupied here. Electrons are occupied this position. One unpaired electron. So this creates, and in the entire capacity. So this type of defect, and this point is called again F center. F center. Always we will ask one question. Define F center. Due to anionic vacancy in metal excess anionic deficient. Anionic vacancy defect in metal excess anionic vacancy defect. The unpaired electron occupies an anionic center. It is called F center. F center imparts color. That unpaired electron absorbs radiation from visible light and it imparts color. And that is called what? F center. Are you clear? For example, sodium chloride is golden yellow. Again, potassium chloride, cesium chloride, all these with pink color, lilac color, different color. So that is called metal excess due to anionic vacancy. If suppose metal excess due to cationic vacancy, we can find in zinc oxide. See, zinc oxide. It's while heating, so it is nothing but a white color. On heating, on just to heat, and you will get zinc, which is 2 plus half O2, and here you will be color imparts. The green color changes to yellow color. So this is nothing but the metal excess defect due to cationic vacancy. Here zinc, which is nothing but zinc, 1 plus X into O. So total number of particles of zinc atom which is more. Cations are more. Cationic vacancy. There is in existence while the formation of a solid, there must be a deficiency. And its formula generally you can write Zn1 plus X. And this type of defect is called metal excess defect due to cationic vacancy. Metal excess due to anionic vacancy you can find F center. Okay, we shall study next part, which is nothing but metal deficiency. Metal deficiency defect. See, metal deficiency. See, in metal deficiency defect, we have an example, iron oxide. Iron oxide. See, actually, iron oxide, iron, so which is nothing but about 0.95 and oxygen, FeO. Here, certain part is filled by Fe3 plus ion in order to complete the lattice. And this type of defect is called metal deficiency defect. What is the example for metal deficiency defect? Iron oxide. So it is a range, it may be a range of Fe 0.93 to Fe 0.96, and generally we call Fe, which is nothing but, see, some of the Fe2 plus cavity is filled by Fe3 plus Fe3 plus. Therefore, it is called metal deficiency. Are you clear? There are metal excess as well as metal deficiency defect. Okay, I will repeat again. The different types of point defects you studied is stoichiometric defect, where the chemistry of the solid remains same, and you have there in non-ionic solid vacancy defect and interstitial defect. In vacancy defect, one of the particle is missed from the lattice and density decreases. In interstitial defect, the one of the particle is missed in one line and it is present in the same lattice in other line. Density does not change. Okay, these are the basic two defects in non-ionic solid. If you go for ionic solid, there are two types of defect. One is Frankel defect and Scotty defect. In Frankel defect arises where in ionic solid, the cation and anion size is difference. Size difference is there. In Frankel defect, so one of the cation is missed and it is present in the same lattice. Therefore, density remains same. In Scotty defect, so equal number of cation and anion are missing. Generally, density decreases. We can give the example. So particularly, silver bromide will show, it can show Frankel defect as well as Scotty defect. Okay, again, impurity defect. So during the crystallization of sodium chloride, if impurities like strontium chloride are present, at that time, certain about 2 particles of sodium atom is replaced by strontium ion. That particular defect is called impurity defect. Example is NaCl and strontium chloride. Again, you studied metal excess due to anionic vacancy, metal excess due to cationic vacancy. Metal excess due to anionic vacancy, an unpaired electron occupies the anionic side, and that particular center is called F center. F center imparts color to the solid. Again, metal excess defect due to cationic vacancy in zinc oxide you can find. So white color zinc can change its color on heating. And again, metal deficiency defect, which is nothing but iron oxide. So as Fe2 plus is present in the lattice, so certain particles are filled by Fe3 plus ion also. So particularly which can be asked for 1 mark. Just you have to read. I will give the notes tomorrow. You have to write complete notes of solid state, read, and you can easily understand. So we shall move on from electrical property of metals. That means in solid state, electrical conductance. We shall study the electrical conductance, which is nothing but the conductivity. See, electrical property. Electrical property. Electrical property. In electrical property, you can find, see, you know already conductors, then semiconductors, and insulators. Are you clear? See, as all the solids, all the materials, any substance, it contains electron. Here, conductivity of metal you have to study. See, the electrons present in valency band, if there is it can easily move to a conduction band. What do you mean by band? See, atomic orbitals, any metal is a part is nothing but an atom. So, the electron present in those atoms, it moves the valence electron, which is called valence band. We can find it as valence band. So, this is nothing but a valence band, and this is nothing but a conduction band, which overlaps. So, this is conduction band, and this is valence band, and which is nothing but a conduction band. See, as the electron present in atomic orbital can form a molecular orbital, and that is nothing but a band. In the band, the electrons present in valence can easily move. You can see in the conductors. So there is an overlapping between these two bands. You can find an overlap. There is no, this is nothing but the overlap. We can find an overlap. And this is called what? Conductors. In conductors, the electrical range is 10 raised to 4 to 10 raised to 7. 10 raised to 7 per meter. In semiconductors, it is 10 raised to minus 6 to 10 raised to 4. So we can find a small gap between the valency band and the conduction band. So this is nothing but a semiconductor. If you go for insulator, there is a large gap between. So gap is large. We can find the gap. Here very small gap. And insulators have the range 10 raised to minus 22 minus 10 per meter. Are you clear? So these are nothing but the insulators. So where the name itself indicates insulator, where electrical conductivity is nothing, there is 0. And in semiconductors, as there is a very small energy gap, these valency band electrons can move towards you. And here there is an overlapping. So therefore metals are good conductors of heat and electricity. Generally metal shows 10 raised to 7 per meter conductivity. Its range is, so metals are good conductors of heat and electricity because the valency band is overlapping with the conduction band. Are you clear? So these are nothing but the electrical property in solid state, particularly in metals, semiconductors and insulators. So you have to study the semiconductor elements and how this conductivity increases. Okay, dear students, you have to remember about the band, and now more you have to study about the semiconductors. So you studied in physics, but which is relevant to your syllabus, I am going to tell within 2 minutes. Say, listen here. In semiconductors, see here the very small gap between valency band and conduction band. So these atomic orbitals, whatever the element present, and it forms a molecular orbital where the electrons present in valency band can move to conduction. And the elements like silicon and germanium particularly silicon and germanium, room temperature they conduct electricity. They conduct electricity. And this type of semiconductors are called intrinsic semiconductor. See, intrinsic semiconductor. And this conductivity increases by adding the impurities of other group elements like 15 group as well as 13 group. If we are add 15th group element to the elements like silicon and germanium, they are called electron rich impurity we are going to add. You know silicon, so this is nothing but the cage of silicon, which is a tetrahedral, where 4 silicon atoms are arranged like this. You can see 4 valency electrons are there in silicon. You know this structure. So this is nothing but the silicon. You can easily understood. See here, silicon has 4 electrons which is paired. It conducts electricity at room temperature, that is called intrinsic semiconductor. But its conductivity is increase, its conductivity will become more by doping it, by adding it with electron rich 15th group element like phosphorus. See, suppose phosphorus is added to this, See, all the 4 electrons are paired and one extra electron you can find. One extra electron you can find. So therefore, its conductivity increases. And this type of see is called N-type semiconductor. These are called N-type semiconductor. They are electron-rich semiconductor. Are you clear? So what are the characteristics you have to remember? In electron-rich semiconductor, the elements like germanium or silicon is doped by whatever the impurity you are adding to increase its conductivity. That process is called doping. That's all. Are you clear? See, when it is doped with the element like phosphorus, so this another 5th electron, phosphorus has high valence electron. You know this. And even you add arsenic also. And that time also, this extra electron, this mobile electron, moves and conductivity increases. When it is doped with a pentavalent impurity, the formed semiconductor are called N-type semiconductors. Those are called N-type semiconductor. Okay, if you go for P-type semiconductor, which is nothing but electron deficient. If silicon is doped with a 13 group element like aluminium, if it is doped with 14 group element like aluminium, then see it has only 3 valence electron. Aluminium has only 3 valence electron, and this is nothing but the hole. And this hole passes the electrons and receives the electrons, and conductivity increases. See here, hole is responsible to increase the current, and this type of semiconductor is called P-type semiconductor. Are you clear? This type semiconductors are called P-type semiconductor. In this P-type semiconductor, the electron deficiency we can find. Hole, whatever the created hole, it is responsible for passing the current. And we have 2 types of semiconductor, extrinsic semiconductor. Those are N-type, which is formed by pentavalent impurity, adding an impurity to the semiconducting elements like silicon to increase its conductivity is called doping. If doping is did by 15 group elements, it is called electron-rich semiconductor, and formed semiconductor is called N-type. If its semiconducting property is increases by doping it 13 group elements like aluminium, The whole coil is responsible for the current. You have to remember the tetravalency of silicon, and that silicon is nothing but a normal semiconductor, and again it is increased, its conductivity is increased by doping it with either electron rich impurity or electron deficient impurity. That much you have to remember. Okay. Again, what are the uses of this NNP type semiconductor? See, these are used to prepare diodes. Again, you studied in physics, and even rectifiers and even transformers. And you have to remember more about these uses. See, if 12th and 16th, and see 13th and 15th, these elements are sandwiched, and we will find the metallic conducting substances. When, see, semiconducting phenomena helps our scientists work. When 13 and 15 group elements are mixed, sandwiched, they form a particular substance which are good conductors like copper and aluminium. See, here 12 group elements, you have again zinc, cadmium. If zinc is the 16 group element, 16 oxygen, sulfur, say ZNS, again CDS, and these are shows conductivity. If you go for 13 group and 15 group, see 13 group aluminium and 15 group phosphorus, aluminium phosphorus mixed, we will find a particular substance which is a conducting material. It is a conducting material. We have a conducting material like rhenium oxide, ReO3. So it is conducting like copper. So these are the uses of semiconducting phenomena. Clear? So particularly you have to study about the semiconductors. Okay. Then we completed electrical property in solid state. In electrical property you studied the insulators, conductors and semiconductors. And particularly you have to study about semiconductors. Electron rich impurity and electron deficient impurity. Electron rich forms N type, electron deficient forms P type. So an extra electron is responsible for the conduction of, and here hole is responsible for the conduction. Okay, last we shall study about magnetic property. Within 5 minutes we can complete the magnetic property of solid state. In magnetic property, see magnetic property, magnetic property. In magnetic property, see every substance, you consider any substance, it has a certain magnetic moment. Whatever may be, it has certain magnetic moment. And that magnetic moment you have to study. How these magnetic moment or magnetic property of different substances shows different magnetism. So what is the reason? See, you consider any substance, it has a tiny small magnetic character. Some material may have large magnetic character, and that particular thing you have to study. Okay, in magnetic property, see, if I am considering lattice here, it contains one of the particle, it may be an electron. See, any substance, if it is magnetic, it is due to the unpaired electron. It is due to the unpaired electron. So, electron has two types of motion. One is orbital motion. Another one is motion towards its axis. Orbital has two types of motion. One is, say, motion around the orbital and motion around the axis. So it is due to the moment of the electron. See, this is nothing but an orbital. So this is nothing but moment of the electron. This is electron. Again, it is towards its axis. It moves towards its axis. Two types of motion. One is orbital motion, and another one is due to motion due to its axis. due to its axis. So any substance, it is magnetic due to unpaired electron. And spin of the unpaired electron is nothing but two types of spin or the motion we can find. One is orbital motion, another one is motion towards the axis. And we will find the magnetic moment. As magnetic moment is more, that is more magnetic material. So those magnetic materials are classified into paramagnetic, diamagnetic, ferromagnetic, ferrimagnetic, and antiferrimagnetic. Are you clear? The magnetic materials are classified into different types. One is paramagnetic. So you are right, paramagnetic, and another one is diamagnetic. You know this, diamagnetic, where the magnetic moment is very less, equal to zero. Then ferromagnetic, and antiferromagnetic, and last one is ferrimagnetic. See, paramagnetic. When a magnetic field is applied to a substance, it behaves as a magnet. If you remove the magnetic field, it never acts as again a magnet. See, that is nothing but the arrangement of electrons in a like order, well order. So you can find it paramagnetic substances. Paramagnetic substance like O2, again Fe2 plus, these are the examples of paramagnetic substances. Diamagnetic substances which are weakly magnetic and magnetic moment is zero, like sodium chloride, water. The magnetic moment is zero, and that is called diamagnetic substances. Are you clear? Another one is ferromagnetic substance. Most important you have to remember. The metals like iron, antimony, cobalt, nickel, and these, if you apply a magnetic field to those substances, it acts as a magnet. Again, if you remove the magnetic field, even after removing, they act as a magnet. Therefore, they are called ferromagnetic substances. In the ferromagnetic substances, each tiny particle, each small particle acts as a magnet. In entire lattice, each particle acts as a magnet, and that is called domain. And all are well arranged like this. See, all are well arranged. Only one direction. You can find it. Are you clear? So these are the ferromagnetic substances. The materials like iron, cobalt, nickel. See, these are when we apply a magnetic field to those substances, they act as a magnet. Even after removing the magnetic field, they will behave as a magnet. And each tiny particle act as a strong magnet. Its magnetic moment is more. So they are called ferromagnetic substances. All domains are arranged in one direction. And another one is antiferromagnetism. See, in antiferromagnetism, the example like manganese dioxide, MnO, like MnO. So you can find the particles like this. So one of the domain is one direction, another is it cancels each other. Therefore, it is called one is magnetic, and its magnetic moment is cancelled by another particle. So therefore, it is called antiferromagnetic substances. Example is manganese oxide. And ferrimagnetic substance. Again, these are highly unequal. See, two domains we can find. So one in one direction, another is another direction like this. See, there is an unequality. We can find these in Fe3O4, Fe3O4, even in zinc oxide, that means we can take Fe3O4 is a particular example. Are you clear? For ferromagnetic, all the domains are in unequal, in one direction another direction is different. So at the time, what is the magnetic moment is, we cannot judge it out. Magnetic moment is unequally, there is no equality, and such substances are called ferromagnetic substances. Are you clear? Dear students, you studied about different types of magnetic properties in solid state. Magnetic property of any substance is due to the presence of unpaired electron. Whatever the electron present, it shows two types of motion. One is orbital motion, another one is motion along the axis. That arises a magnetic moment in any substance. So those magnetic moment, by considering all the materials, magnetic materials are classified into different types. Those are paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. As O2 and Fe2 plus are paramagnetic substances, diamagnetic, sodium chloride and water, ferromagnetic, here we have to study each particle is act as a dimagnet. So therefore this is called a domain. Then another one is antiferromagnetic material, where one is in one direction, another direction is cancelled in opposite direction. Therefore this is called antiferromagnetic substances. Example is MnO. Another one is ferrimagnetic, Fe3O4. Okay. So dear students, last another one class for the calculation of problems on repetition I am going to take, and tomorrow I will send the notes. So this completes our topic solid state. Okay, thank you.